Hi, welcome to the Data Engineering with Spatially Enabled DataFrame and ArcGIS API for Python session. My name is Mohit Agarwal and I'm a product engineer with the Python API team. And I also have Andrew Chapkowski with me. Andrew.
Hi, my name is Andrew Chapkowski, and I'm the lead developer of the ArcGIS API for Python. We're going to go ahead, before we get started, we're going to talk about what is the ArcGIS API for Python. The ArcGIS API for Python is a collection of modules that follow the PEP8 pattern. It all starts with your GIS object that's going to allow you to connect to your enterprise or ArcGIS Online. And the GIS is going to give you capabilities to work with analysis. It's going to also allow you to work with specific apps such as dashboards and widgets. And then it allows you to work with specific products such as ArcGIS Server, Mission Server, Notebooks, and Enterprise. And as our product line grows, so too will the ArcGIS API for Python. But this topic is only going to cover a small section of that, and that's specifying on the parts on the bottom. And that's with the spatially enabled data frame. Now we're going to start with Mohit taking it away, giving us some background information, and then we'll see how we can use GIS with this amazing dynamic in-memory object. Take it away, Mohit.
Thank you, Andrew. All right, let's start with Pandas. So Pandas provides high-level data structures and functions that are designed to make working with structured or tabular data fast, easy, and expressive. It sort of blends the high performance of NumPy with data manipulation capabilities of relational databases. Pandas provides sophisticated indexing functionality that you can use to slice, dice, or reshape your data. And it also provides capabilities to handle missing data and create plots. So today we are going to talk about two main data structures of Pandas. One is a series and the other is a data frame. We're going to look at a high level on how we can create a series and access its elements. And then we're going to dive deep into the data frame where we will look at creating a data frame, importing data into a data frame, navigating and operating on a data frame, how to work with missing data, and how we can plot the data using Pandas. So let's jump to the code. So before we get started, let's talk about installation and import. A typical installation of Python API comes with Pandas, and we can just import it as this statement, import pandas as PD. And this will import Pandas into our system. Now, like I mentioned earlier, we'll discuss two main data structures today. Series, which is a one-dimensional array, labeled array that can hold any type of data, such as integers, strings, floats. So as an example, you can look at a list of items, which can be a series. Data frames, on the other hand, are two-dimensional with labeled axes. So you can think of it as a table on an Excel spreadsheet or a SQL table. We'll start with the series. So series, as I mentioned earlier, is one-dimensional array of indexed data. So it contains a sequence of values, and then each of those values contains data labels called an index. Let's start by creating a series from a list. So here we have a list of heights. And we can create a series using the pd.series function and pass this height list into it. So the results show the values that we have in the series, and along with those values is an index. This is the index. We can check the type of this S1 variable using the type function, and we can see that the type of this is pandas.core series. We can access individual values or index of a series using the values and index attributes. So here we can access values, just the values using s1.values, and then we can access the index using s1.index. Now let's look at accessing different elements of a series based on the index that is associated with the series. So let's quickly look at the series itself, and then we can access its elements using the index. So if we want to access the element on the 0th index or the 3rd index, we can specify the index in square brackets and then print the elements. So we see here that the element at the 0th position is 176.7, and at the 3rd index position is also printed. Similarly, we can access the elements based on a range of index positions using the colon notation, and we can also perform reverse indexing to get the last element. Here's the last element. So this was a high-level overview of how we can access elements and create a series. Let's talk about and dig into the details of a data frame. So a data frame represents a rectangular table of data, and it contains an ordered collection of columns. As example could be a SQL table or a spreadsheet table. Each column in a data frame has a column name for reference, and it can be accessed using the row numbers or the index of the record. Each column in a data frame can be also of a different value type. So it can be numeric, string, or Boolean, and so on. Let's start with creating a data frame. Here, we're going to create a data frame from a dictionary. So in this cell, we have a dictionary called data, which has state, year, and population as the dictionary keys and the values for each of these keys. We can use the pd.dataframe function to create a data frame. Here in the results, we see the data frame itself with 3 different columns, and then each record has an index associated to it. So this is one way of creating a data frame. We can create data frame from arrays, from series, from lists, and so on. Now let's look at importing data into a data frame. One of the most common workflows in data science and analysis is to import data from outside, from CSV files, from JSONs, Excels, and Pandas provides the ability to read the data from all these formats. Today, in this example, we're going to use this COVID nursing home dataset. So we'll use a subset of COVID-19 nursing home data from the Center of Medicare and Medicare Services. Now this dataset has been curated for illustration purposes, and it does not reflect the exact data on the CMS website. So we're going to start with reading the data from a CSV file. We'll use the pd.readCSV function and specify the location of our CSV file and run this cell. Now data may contain a number of rows. It may contain thousands of rows. So to look at the first few rows of the data, we can just use the .head method. And we can do coviddf.head, and here it returns the top 5 rows of the data. So let's take a quick look at our data itself. This data contains a name of the city, provider state, and then some data on COVID. So it has COVID admissions, COVID cases, suspected cases, all deaths, and COVID-19 deaths for these nursing homes. We can also get, if we want to get, let's say 20 records as a head, we can specify the number of rows that we want, and this function would return those number of rows that is specified in the head method. Now, each of the columns in our data can be of a different type. So to check the type of data we have, we can just use the dtypes property of the data frame. We can do coviddf.dtypes, and it returns the data types of each column. So we can see provider city and state are object, and the rest of the data is float. Now to check the number of records and the number of columns in our data, we can use the .shape property of the data frame. So here, running this cell, we can see that this data set has 90 records and 7 columns. So to quickly summarize, so far we saw how we can create a series and access its elements. We also saw how we can create a data frame and then import data into a data frame using a CSV file. Now let's talk about navigating a data frame. So elements or subsets of elements in a data frame can be accessed in multiple ways. We can access these subsets by location, like we do in lists, by labels like in dictionaries. We can create Boolean masks, or we can use special indexing operators such as lock and ilock. Let's start with selecting columns. Columns in a data frame are essentially series objects, and we can access these using dictionary style indexing. Let's first look at the head of our data again. Now to access a particular column, we can just specify the column name inside the square brackets along with the data frame. And here are the results of the confirmed cases column. We can also use attribute style access, in which we can use the dot notation to specify data frame dot column name. And here we can see the results of the data in the all deaths column. So this is one way of selecting columns. The other way to subset the data is to use lock and ilock operators. Lock is used for label-based indexing, where we subset by specifying the index and column names. Ilock, on the other hand, is for positional indexing. Here we can subset the data by specifying index and column position. Well, let's start with selection using ilock. Let's again quickly look at the head of our data. Now let's say we want to select the first 2 rows and all columns. We can use the ilock operator for this. And within the square brackets, we can specify the number of rows we want to subset and the number of columns we want to subset. Here in this case, we want the first 2 rows, and we have specified that here. And since we want to specify all columns, we'll just leave it as a colon. And the results show the first 2 rows and all columns in our data frame. Similarly, let's say we want to get a middle subset of rows and columns. We want the second and the third row, and we want the second and the third column. Again, we can use the iloc operator and get the respective data. We can also perform selection using lock operator, which is for label-based indexing. So let's say we want to select the columns from provider state until all deaths. Here, instead of specifying the column position, we specify the name of the column and use the lock operator. So here we specify provider state and all deaths column, and the result is all records and columns from provider state to all deaths. We can use lock operator with index as well. If the index is labeled, we can specify index to subset records as well. Lock and iloc operators allow us to subset the data, but let's next look at the query operation, which allows us to perform conditional selection. So query allows us to select elements of a data frame that satisfy some condition. So let's say we want to look at all the records where COVID cases are greater than 70. Such operations, such conditional logic can be worked using the query operation. Query uses string expressions, and it's very similar to the where clause in SQL. The main benefit of using query is that it's more efficient and it uses less memory than pure Python operations. Let's take a look. Let's look at the head of our dataset again. Now let's say we want to get all the records where number of confirmed cases are greater than 70. For this, we can use the query operation along with the data frame. So we can do covidDF.query. And within strings, we can specify our condition. Here, the condition is confirmed cases greater than 70. And these are all the records where confirmed cases are greater than 70. We can do multiple conditions as well. So let's say we want to look at the records where confirmed cases are greater than 70 and COVID deaths are greater than 50. These two conditions can be added into the query operator using parentheses. So the first condition will go in the first parentheses. We can use the AND operator, and the second condition can go in the second parentheses. We also see these backtick operators. These backtick operators are used to escape any special characters in the column names. So here, since this dash or is a special character, it is treated as a special character, we can use backticks to escape this special character to run our query correctly. And the result here shows all the records where confirmed cases are greater than 70 and then COVID deaths are greater than 50. So we looked at how we can do, we can select subsets of data, or we can select based on conditions. We can select data based on certain conditions. Now let's look at operating on DataFrame. We'll start by combining data. One of the most common workflows that we'll see in data science is to combine data from various sources. We may have data from different CSV files, feature layers, different APIs, or SQL tables that we would want to join. And there are numerous ways to join the data. You can use concat, you can use append. Today we're going to look at the pandas.merge function that allows us to join the data frames based on one or more keys. So merge works as a standard entry point for all database join operations, and it can handle SQL join operations such as inner join, left join, outer join, and so on. Let's take a look. So before we join, we'll need another data frame. So here we read another data set that we have created from the CMS nursing home data set. This data set is about the number of beds at these facilities. Let's read this data and take a look at the shape and head of this new data set. So this new data set is stored in the beds df variable. It has 90 records and 6 columns. And it has a city column, state, all beds, occupied beds, and longitude and latitude for these providers. Now let's take a quick look at our COVID data frame as well to see what we have been working with so far. So COVID DF had 90 records also. It has 7 columns, and here are the details of the COVID data frame. Now let's say we want to merge these two data frames. To merge these, we need common keys, and the common keys in these two data frames are the city and the state columns. There are no duplicates. We have created the data frame so that there are no duplicates in city and state, and a combination of city and state is unique. So let's merge the data. So we are going to use pd.merge function and specify the two data frames we want to merge. Here we'll specify the COVID DF and then beds DF. Now we're going to specify the columns we want to merge on. And since our column names are different, we're going to use left on and right on parameters. In the left on parameter, we'll specify the column names for the left data frame, which is the COVID DF. And then in the right on parameter, we'll specify the column names of the right data frame, which is the beds DF. Now in the how parameter, we specify the type of join we want this operation to use. Here we'll use an inner join. Now that this operation is done, let's take a look at the shape of our data and the columns that we have in this data set. Here we can see that this data set now has 90 records and 13 columns. So instead of 7 or 6, now the two data sets have been merged and we have 13 columns. And here's the list of columns that we have. So we have provider city, state, we have the COVID details, and then we have city, state again. So there is duplication in data. So even though merge the two data sets, it kept the columns from both data sets, and we have duplicate columns. And you will often see that data is duplicated in your data sets, and you have to drop the data, or you have to drop some columns for some other reasons. And in those cases, the drop operation comes in handy. So let's take a look at how we can drop the data. So drop by default works on records, but we can also specify the axis equals columns parameter to make it work on columns. Here in this cell, we use the drop function and specify the columns we want to drop, city and state. For axis, we specify columns to drop the columns, and then we specify an in-place parameter equals true. In-place is specified so that the drop function by default returns a copy of the data frame. In order to perform this operation on the data itself, we specify this in-place parameter as true. So here is the head of our data, and we see the provider city and state columns. We don't see city and state columns themselves, so these have been dropped. So to quickly summarize, in the last couple of sections, we talked about how we can navigate through a data frame. We saw how we can select columns using lock and iLock, and then conditional selection using query operation. And we also saw how we can operate on a data frame, so how we can merge data from different sources, or how we can drop the data. Now let's look at dealing with missing values, how to work with missing data. So real world data is rarely clean. It's for the most part, your data will be messy, and you'll see a lot of null values in the data. These values are referred to as null, nan, or na values. There are various methods for detecting these null values, removing them, or replacing them. Let's get started. So we'll start with detecting missing values. IsNull method can be used to detect and filter missing data. We can just use it with the data frame itself and do covidDF.isNull, and this returns a data frame with true or false results. The false indicating that there is no missing value, and true indicating that there is missing value. Now the result is not very interpretable. So one way to read it or to make better sense of it is to chain a sum operation to it. By chaining a sum operation, the result returns the number of missing values that we have in each column. So here we can see that columns from COVID-19 COVID admissions all the way through occupied beds have missing values. We can also look at the total number of missing values in a data frame by chaining another sum operation. And doing this, it shows that this data set has 49 missing values in total. Now there are multiple ways to handle missing data. We can drop it, or we can impute the missing data. Let's start by dropping missing data. Drop NA function can be used to drop missing data. Like the drop function, this drop NA function returns a copy. So if we want to perform this on the data frame itself, we'll have to specify in place equals true, which we are not doing that here though. So running this returns a copy of the results, and here we can see that the returned data frame has 62 rows. So instead of 90, we only see 62 rows, and the records that had null value have been dropped. Dropping null data is not recommended, as it reduces the number of records that we have. It reduces the data that we have. A better approach could be to impute the missing values. Let's take a look. We can replace missing values with constants such as 0 or 5 or a string value. Or we can also replace them with a mean, a median, or any other aggregate of our data. And fill NA can be used to perform such operations. So let's start with replacing with a constant value. And here we use covidf.fillNA and replace the missing values with NA. This can be anything. This can be 0, 5. I'm specifying NA so that these missing values are highlighted. So we can see here that this record has a missing value. There's another missing value. Here's another one. Now, instead of filling with a constant, we can also fill specific missing values for particular columns based on their aggregates. Let's take a look. So here we create a fill value dictionary where the dictionary key is the column name and the value is the aggregate for that column. So here it's a mean of COVID admissions. For all deaths, we are taking the median of COVID deaths. And for all beds column, we are just going to replace it with a constant value of 100. And we can pass this fill value dictionary in the fill NA method. So within fill NA, we can pass this dictionary, specifying place equals true, and this replaces the missing values in the data frame. And we can check the total number of missing values in our data again, and we see that COVID admissions column, all deaths column, all beds, none of these have missing values anymore. So we have looked at how to deal with missing data. Now let's see how we can quickly plot data using Pandas DataFrame plot function. So let's take a quick look at the head of our data. Now to quickly generate some plots from the data, we can use the plot function. If we want to plot, let's say, for a numeric column, we can subset the data for that column. So we specify COVID DF and we subset for the confirmed cases column, and then use the plot function, and here it generates a line plot, a basic line plot of confirmed cases. We can also create a better visualization. So we can use covidf.plot and dot the plot type, here's scatter. Then we specify the X and the Y coordinate columns for the X and the Y coordinates. And we can change the figure size. So instead of the default, we can specify a figure size and give this a title, this plot a title as well. So here is a way of generating that. We can also create subplots. For creating subplots, we'll have to import matplotlib. So here we import matplotlib.pyplot as PLT. And then we create a grid of plots. So here we create a 2x2 grid, and the total figure size we specify is 15 by 10. Now that we have created a 2x2 grid, we can add 4 plots to this grid. So here we add a line plot, a scatter plot, a histogram, and a blocks plot to the grid. And the result is a grid of all these 4 plots in a single frame. So to quickly summarize, in the last couple of sections, we talked about how to work with missing data. So we saw how we can detect, drop, and impute missing data. And then we saw how we can generate some quick plots using Pandas. Now, Andrew is going to talk about spatially enabled data frames. Over to you, Andrew.
Now, the spatially enabled data frame, just like we saw before, is built upon Pandas, except it has 2 unique namespaces. One's called Spatial, and think of that as operations that occur on the data set as a whole, and then it has what's a namespace called geom. And these are operations that are going to occur on the one-dimensional series that contains your spatial information. It also has a custom type called geometry. It provides a different experience to working with geospatial information. Everything is contained in memory, so it's fast, and it has on-the-fly indexing, and it's supported across multiple platforms, not just Windows. So let's take a look at how our custom namespaces work. For using geom on our series, you would take your df dot, in this case, the default geometry column is called shape, so shape, and then you would do your dot geom, and then you would get access to all your spatial operations that would act on a single geometry for each row. For the data frame as a whole, you would do dot spatial. So let's say we want to reproject our data. So we would take our data frame object, dot spatial, and then say project as, and we put in our WKID, in this case 4326 WGS 1984. I mentioned some of the benefits of it being cross-platform, but what that means is that you can do spatial operations and the same operations on Macs, Linux, and Windows. So it's platform agnostic, and you can start accessing and working with spatial information in a spatially enabled data frame without actually being on any of these machines, and the workflow should work across the board. It supports multiple geometry engines. So if you have a user that has ArcGIS, and then you have another user that is on a Mac and they're using Shapely and Geos, those operations should work the same across the board. And the user should never know what the geometry engine is on the back end. For reading and writing, you can use Fiona, Shapefile, or ArcGIS to read and write your data. Let's go ahead and get started. If we only want to import the accessors, those two namespaces, we can import it like this. We can say import pandas as PD, and then we're going to do from ArcGIS.features, import GeoAccessor and GeoSeries accessor. Now our namespace is registered, and it's recognized when you create a data frame that those will exist. Now we're ready to consume data. And the API allows you to consume a whole host of information. It can be existing Pandas data frames, feature classes, which includes shape files, file geodatabases, enterprise, tables stored within Postgres or something like that, and even feature layers and map services. One way we can consume this information is, let's say we have a feature layer. We can go ahead and instantiate that as a feature layer object, and then we just do pd.dataframe.spatial, and then you could say from layer and pass in that feature layer object. If you have a feature class, you could say from feature class on our spatial namespace and pass in that path. And we can also consume information from other Pandas data frames. So we can read a CSV from a URL. In this case, it's the USGS earthquakes feed. And then we could say we're going to convert that XY data with latitude, longitude, set our spatial reference, and now we have a spatially enabled data frame. We can turn around and persist our information multiple ways. To persist it as a feature class, we can do toFeature class. If we want to take our spatially enabled data frame and save it out as a table, we could say toTable. If you want to save it out as a service, we can do gis.content.import data. When you do gis.content.import data, you have to be an authenticated user. Let's look at working with our one-dimensional array or a Pandas series. So we're going to read in information from a local shapefile that I have, and this one's a zoning data set. And we're going to go ahead and do pd.dataframe.spatial.from feature class, import our path. And then we're going to look at the first 5 records, or the first 5 entries within our shape column. And we can see that it's Esri geometry and it has the rings, and it shortens it up for so the whole thing doesn't print out. We can go ahead and do operations with that column right off the get-go without having to recreate the table. So let's say I need the centers or the centroids of this location. So I can go do SDF.shape, which is my geometry column, do .geom, which is that geometry namespace, and then centroid. And we can get back the center locations for each of those polygon geometries. We can go ahead and then also calculate the area on top of that. And there's a whole host of other functions that you can do as well. So I'm going to say I want to do a planar calculation, and I want my summarization in acres. And then at the end, I'm going to summarize all the numerical values within that geometry column. And we can see that the total area of this feature class in acres is 7,207 acres. The spatial namespace provides data set level operations. And so that means you get data set information. And this is where the I/O, the read-write operations exist. Let's take a look. Let's reload that data set back in, the zoning data set, and we can look at the bounding box. Within Jupyter Notebook, certain operations that involve geometries, when you display them within the cells, you'll get back this graphical display. So the bounding box is a square, which is expected. But let's say you want to know the numerical values. Well, you can do .full extent off the spatial namespace, and you get back the full extent of our data set. We can do on-the-fly reprojecting. So we can see the default projection is 102,667, but let's say we want to reproject it into WGS 1984. So this is a data set operation. So we can do sdf.spatial.project, and then it'll create the new data set within 4326. And this is an in-place operation, so there's no need to recopy your data. Besides doing spatial operations with the spatially enabled data frame, we can also do visualization. And there's a rich visualization library associated with this, and it all goes through the plot function off of the spatial namespace. We made the choice to mimic the syntax very similar to matplotlib for visualization. So it should be very familiar for Python users on how to get started and drawing geographic information on a map widget. There are multiple renderers that we support within the spatially enabled data frame. The most basic is simple, and that's a single color. And then we support unique and unique with arcade. And this will render information based on a unique value. This is suitable for categorical columns. Then we have class break information, and this is suitable for numerical columns. And then we have heat map, which renders based on density. There's helpers within the API to assist you to understand all these rich visualizations that we have. So let's say we're working with point geometries. We could say show styles point geometry, and it returns back a data frame. And here you get your marker symbol, and that's the shortcut you'll pass in, but we also have a description of the Esri style of what it associates to. So an O is associated with circle, a plus is associated with cross. We also have a whole set of color maps that you can choose your colors from if you don't know which ones you want to use. And you can see these by calling display color maps, and it'll print out all the available color maps and names associated with the API. Now let's see some examples of doing simple rendering of data. So I'm going to connect to my GIS. First I'm going to do from arcgis.gis, import GIS. Then I'm going to do GIS equals and connect to my online profile. I'm going to create a map called first map, just have it be of the world, set the base map, and display it within my Jupyter notebook. I'm going to pull an item down. I'm going to do gis.content.get and grab it by its item ID, get the first layer within that item because I know it has at least one layer, and then I'm going to query. And this is how I'm going to get my information from that feature layer into a spatially enabled data frame. So I do feature layer.query. I'm going to pass in a where clause, and then I set this as df equals true, and this will pull the information in as a spatially enabled data frame. Once I have the information, I can then go ahead and look at it. So I'm going to do df.head, which will give me the first 5 records by default. And we can see it has the columns, as well as we can see that we're getting back shape type of points. To visually see this information, I'm going to do df.spatial.plot, pass in my, say, map widget equals and first map. And if we scroll back up, we can see our points show up on the map, just like we would if we were to plot a feature layer. And we can interact with it the same exact way we would expect also with a feature layer on the map. Let's dive a little deeper and look at some more advanced rendering techniques. By default, the spatially enabled data frame, if you're pulling information from a feature layer or a map service, the spatially enabled data frame will inherit that rendering information from the service. That's if you don't pass anything. But let's say we want to override it. I want my symbols to be square, and I want to change the color pattern to use the red reversed color map. So I can specify, I do map widget equals my map object. I can say I'm going to use a simple type, renderer type, my style of square for S, a color ramp, my outline color that I want to pull from, and then the size. And let's go ahead and plot that on the map. Our data now shows a little different. We have the squares showed up on the map as expected with the outline, the inside red, and the outside is a yellowish color. For class break, we can do class break and unique renderers. Let's take our same data, and instead of passing in an S for the simple renderer type, we're going to pass in a renderer type of U and specify our column. Now it's going to, because we didn't specify a color ramp or any color information, it defaults to jet, just like it does in matplotlib, and it plots it on the map. And now by itself, you really can't, it's different colors, but you don't know what those colors mean. So we can do m3.legend equals true, and we can see how each color is associated with a specific value. We can do the same thing with class break renderers. So now we're going to be using numerical columns. I'm going to plot my data. I'm going to say class render C for class breaks. We're going to use the method of Esri classified natural breaks, set our count, a column, color map. And you can see it populates our data with the associated class breakers on it. And we can do legend once again to see how it broke up the different classes. It's not just point data that we can render, so I'm going to pull in a feature layer, query it. I want the output to be in 4326, set it as SeDF equal to true. And we're going to look at, we can also plot polygons and polylines. So here's just an example of doing class break render with natural breaks for polygon data. I mentioned before that we can use spatial indexing on the fly. There's two types of spatial indexes that are supported with spatially enabled DataFrame, arctree and quadtree. Spatial indexes are going to allow us to find spatial information quickly, but it's a generalized spatial search. So if you have a complex geometry that has lots of ins and outs, you might get extra information that you don't want. So it would be a two-part step. And we'll go through and show how that works. We're going to pull in some information, and these are the major US cities as points. And we're going to query our data. Once again, we're going to query all records, and we're going to set the output to be 4326, so WGS 1984, and SeDF equal to true. Now we have spatially enabled data frame. By default, we don't have a spatial index, and since that's a data set operation generating a spatial index, we're going to do sdf.spatial.sindex and set our type. In this case, we're going to use quadtree, and now we have our index object. If I want cities only within the state of New Jersey, let's say, I can do an index.intersect, pass in my extent, and I'll get back my results. So let's see how well we did for the New Jersey cities. I'm going to create a map, zoom into New Jersey, and then plot my results on the map. We can see that because New Jersey isn't perfectly square, we got areas outside of New Jersey. It has a point up here, and down here in Cape May, it sticks down. So our square doesn't fully represent just the area of New Jersey. We end up getting Delaware, Pennsylvania, and New York as well, and we don't want that. So how can we get rid of that information? So let's go back and get some more information. In this case, now I'm going to connect to ArcGIS Online. And I'm going to pull down some information that's provided by New Jersey's Office of GIS for a New Jersey boundary file. And I'm going to pull that information in and get that geometry. Once I have that, I can do a secondary query on our data from the initial search that we did and pull out that information. So I'm going to do our extent cities, which we did right here. And that was our initial query using the spatial index. And I'm going to do shape.geom.disjoint equals, and pass in this geometry and set it equal to false. And that's going to mean what this query states is that if it intersects, or if it is not intersecting, then return true. So that means it is intersecting. We're going to pass the result of our query into our data set and then plot it out on the map. And let's see how well we did now. We can see that we got rid of all the information outside of New Jersey by doing those two steps. So we got rid of Delaware, Pennsylvania, and New York. Now the spatially enabled data frame isn't just about doing work with doing visualization. You can also do analysis with it, and we can pass it into tools directly. So let's go ahead and take a look at an example here. We're going to do from ArcGIS import create viewshed, and then we're going to grab some information, some of those cities we had before, and display it. We can then pass that information in and pass it in as a feature collection, and then do our results, and then we can go ahead and visualize the results on the map. Because we didn't specify an output, we get back a feature collection, which is a JSON representation of our information, and nothing is persisted online. Now we're ready, we can go back and add our results back to the map, and we can see that we get our areas. Let's zoom into one over near Scranton, PA. And we can see our viewshed from this location that we had there. We can also pass in spatial image data frames directly into enrichment, and when we get back a piece of information, we also get back a spatially enabled data frame. So we can say from arcgis.geoenrichment.enrich, do enrich, pass in our study area, say the collection of information we want, and then display it. We can also turn around and display that information on the map. And notice we get back polygons with point data when you pass it in, because when you do an area search of points with geoenrichment, you get back a polygon buffered by a minimum of 1 mile. Now I want to flip over to an application of using spatially enabled data frame along with other parts of the ArcGIS ecosystem. And our goal here is to assess and access to public transit. And in this use case, the city of Chattanooga, Tennessee is considering adding a new bus route, and they need to decide the areas of most need. It all starts first by setting up our environment. So we're going to import our Pandas and ArcPy. From ArcGIS, import GIS, and then connect to our GIS. We're then going to convert our GTFS, which is our existing stop data for the general transit feed information, and save it out as a file geodatabase. We can also examine the various stops that we have by just reading it directly into Pandas by doing pd.readcsv. We're going to convert our information using the arcpy.conversion.gtf stops to features data and save this information out as a feature class. We can then visualize the stops that we currently have for the city of Chattanooga. Next, we're going to do some analysis, and we're going to create drive times for each one of our stops. And we're going to use the travel mode of walk time and the break time of units. We're going to say that we want to dissolve the areas, and we want to see how far people can walk within 5 minutes, because we don't want people walking more than 5 minutes to our area. Once we get this information, we're going to concatenate both of our results into a new spatially enabled data frame, and now we're ready to determine our future bus stops. Using the Living Atlas and geoenrichment, we can attain our census information. So we're going to pull down the block groups for the city of Chattanooga and query out the area that we need. This will give us a spatially enabled data frame. Once we have that, we can go ahead and visualize our area on top of the area with our stops. To get the census information that we're interested in, which is total population and some poverty statistics, such as households with cars and above the poverty, and information about who's above the poverty line, we can pass that information into the enrich method. So we're going to do study area, pass in our block, spatially enabled data frame, and then get our analysis variables that we're interested in. This will give us back a spatially enabled data frame with our information attached. We're then ready to go ahead and do some simple calculations to figure out the neediest areas. We're going to create a spatially enabled index, perform some calculations to figure out the population density, the stop count, the stops within each block, and the stops per person within that block. Once we have that, we can remove the areas that we're not interested in, that have well coverage. Using the query syntax of a Pandas data frame, we can select out information that has a high population density and low coverage.
Thank you, Andrew. Andrew just walked us through working with spatially enabled data frames. All of this information and a lot more can be found in our guide series on Introduction to Data Engineering and working with spatially enabled data frames. The guide series are available at developers.arcgis.com/python. You can also visit our GitHub page for any ideas, issues, or enhancements. Thank you for attending the session today. We ask that you please fill out a survey and let us know your thoughts on the content.
All right, and thank you everybody for watching. We're going to go ahead and answer your questions. You can continue to post them in the chat if you want as we go through, but we have some questions that we've been answering along the way and some we're going to talk about as we go along. First question comes from Vladimir, and he asked, what's the best way to convert a data frame to a file geodatabase? The spatially enabled data frame has the ability to do a 2 table and a 2 feature class. If you specify your output path with the feature class name to a GDB, so a file geodatabase, it'll write it there. Same with the 2 table. So no need to go through the NumPy array to table function. Second question we have is that, is there a data size limit when using Pandas on large data sets? And it gives an example. It says, for example, is processing 72,000 plus census tracts viable? Well, the question is a little complex to answer because it comes down to how big your machine is and what you're able to handle. If I was going to do this analysis on, let's say, a Microsoft Surface that my wife uses, I would not be a viable method. If you have a fairly robust machine, you can figure it out. As a point of reference, I've loaded for point data of over 21 million points into memory and able to work with it efficiently within a Pandas data frame. The next question that I want to talk about is when loading the SeDF into ArcGIS Online as a feature layer, they'll name the columns properly if you have Pro installed, but if you don't, it truncates it. And this is true. It's because we use shapefile or PyShape on the back end, and shapefiles have a limitation there. DBFs have a 10-character limit, so you have to be very careful with your naming conventions if you're not using Pro. All right, Mohit, did you want to take the next question?
Sure. Let me see which one was that.
I can take another one that we just got in. Thank you for asking it. The question was about working with projections on the spatial data frame and doesn't maintain the metadata when sending it back to the feature class. And the answer is yes. If your geometry is projected into a geometry, it'll derive that information from your spatial data.
All right, so I'm going to take this question, Andrew.
Sure.
So we have this question about combination of series data, and the user has 3 series. How do I generate a combination of each element? So you can combine a series. You can create data frames using series. The data frame, the series can be combined to create that data frame, and then you can work with the data frame if that's the question you're trying to ask. We do have these the workflows in the data engineering guide series, which you can find the link in the announcement, and I can post the link here as well. So you can easily combine the series to form a data frame. Do you want to take the next one, Andrew?
Sure thing. So the question comes from Abigail, and it says, should you always work within data frames instead of just attribute tables? It's sort of a generic question. If by attribute tables you mean feature classes, one of the advantages of using a Pandas data frame over just a flat table, especially a shapefile or a file geodatabase, is that your data is very malleable and pliable. That means you can work with it, and it's a snapshot of your data without affecting the underlying data. So if you need to add things to it, take away, do manipulations on columns, you can easily work with that information and never actually have to manipulate the underlying table. So for that aspect, so doing things like feature engineering, working with a Pandas data frame is, has a lot of advantages. Gone are the days with a Pandas data frame or a spatial enabled data frame of having that. We've all been there, whether you're old like me, with coverages, coverage 1, coverage 2, or shapefile 1, shapefile 2, or feature class 1, feature class 2, that they all go away because now we have these in-memory snapshots of our information that we can go ahead and manipulate it. So yeah, I'm going to take the next question. It's from Anonymous, and it says, what is the future of the ArcGIS library versus ArcPy? Is ArcPy going away? And ArcPy is not going away. Actually, these two libraries are symbiotic. They work well together. And if anything, they're going to get closer together. That means we're going to be able to pass information easier between the ArcPy library and the ArcGIS API for Python library as well. They're only going to grow stronger together and be able to make your workflows even more powerful.
Andrew, we have another question on spatial joins, about joining two. Can we perform spatial joins with 2 spatial data frames? And I think the answer is yes. You can perform you can join 2 data frames that have spatial content in them. One of the things I've noticed is depending on the type of spatial data you have, if you have a polygon versus a point data, and the merge you're trying to do, the join you're trying to do, it'll retain the dominant data frames shape features. So if your polygon is on the left and the point data is on the right, it'll take the polygon features. Do you want to expand on that, Andrew, or correct me in anything?
No, Mo, you did a great job explaining it. You can do the features. You have to respect the operations that are being done and how you're doing your join, and what's going to come in and out for that spatial join based on your input geometry. And the devils are in the detail for that. But you can go ahead and take a look at that information. It follows the standard operations, the spatial operations that follow through with ArcGIS geometry objects. For a numeric value is an on-class method rather than classification method. Is there a way to accomplish this within the mapping method you showed? Is it possible in ArcGIS Inline JavaScript API? Do you want to take that, Mohit?
Let me see. Classification. Let me take a look at this, and I need to research, take a look, and then respond while we have some other questions.
For that question, could you just please reach out offline and we'll get back to you. Then we had a question from Brent. It says, does the SeDF support two-feature class enterprise geodatabase? And the answer is yes, you can write to an enterprise geodatabase if you have ArcGIS. There's a question about containerization from Anonymous. He says, do you have any tips for containerizing scripts that use ArcGIS due to licensing? Right now with the containers, you could use Notebooks, which has a runtime, which is a Docker container for that requirement there. Let's see. We had a question from Anonymous about spatial indexes. Are they enabled for spatial data frames? By default, the spatial index that's generated is not created when the data is loaded. It is created on demand.
All right, then we see another question. Andrew, do you know if we have a translation utility that goes from SeDF to ArcGIS?
Right now, the translation utility to convert between the spatially enabled data frame to ArcGIS is to convert it to a feature class, and then you would input that input directly into a tool. We're working on that to have direct, being able to directly consume spatially enabled data frames, but it's just not out yet.
Where for now, the user can convert it to a feature class and then import it in Pro or another tool.
Okay. Let's see. We have a question from Jason talking about asking about mathematical transformations are faster in DF than doing it via ArcGIS, such as doing reprojections. It's not always safe to assume. There's a lot of factors that go into that. So the answer is maybe. We have a time for a few more questions if anybody wants to ask anything.
Right. And then let me see if I can find, I think the user mentioned another.
All right, well, I want to thank everybody for coming today. My name is Andrew Chipkowski, and Mohit, my colleague. We both want to say thank you very much for your questions and attending, and we We look forward to having you guys continue the conversation. We have a GitHub page on github.com/Esri ArcGIS-Python-API, where you feel free to log any questions, issues, or concerns you have with the API. And the developers like myself and Mo, we look at those directly. So once again, thank you very much. Enjoy the rest of the conference. We look forward to your questions, and we'll also be in the Ask Your Expert area if you have anything you want to follow up on. Thank you very much. Have a great day.
Thank you.
Bye.
Thanks for joining us.